Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 5 for January 2025. Let's begin with the first question. In question 1, which species cannot act as a ligand in the formation of a complex ion? To be a ligand, it should have a lone pair. And of course, this one has a lone pair, this has a lone pair, there is a lone pair nitrogen, but here there isn't, so A should be the answer. There is no lone pair to be donated in a dative covalent bond. In question 2, an aqueous solution of a transition metal ion absorbs frequencies of light corresponding to green, yellow, and red. Which ion is likely to be in the solution? If it absorbs these three colors, then it means it's going to appear blue. So I said copper solution absorbs red, yellow, and green, so it appears blue, and that is going to be the answer. Then in question 3, the first 5 ionization energies of 4 elements are shown, which are the ionization energies of a transition metal. So when we look at the first, we see there is a bigger jump here, and that cannot be a transition metal. This could be group 1. And then in B, there is a big jump here. This is going to be group 3. There is a big jump here, group 2. But when we look at the last one, we see there is no major big jump, and this could be possibly a transition metal, so the answer is D. In question 4, what is the color of vanadium 4 ion in aqueous solution? It's going to be blue because you remember the colors. Vanadium 5 is yellow, 4 is blue, 3 is green, and 2 is purple or sometimes violet. Then in question 5, which statement about a catalytic converter used to reduce toxic emissions from internal combustion engines is not correct? They say it contains platinum. That's correct. This is one of the catalysts that can be used. The others could be rhodium and palladium. And then in B, carbon monoxide and nitrogen monoxide are absorbed by the catalyst. No, it does not absorb. So this is wrong. And then after the reaction, desorption of these two gases takes place. That's true. It is a heterogeneous catalyst. That's true because gaseous particles are reacting on the surface of a solid catalyst, so it's heterogeneous. In question 6, which of these pairs of elements are both transition metals? To be transition metals, it means they have partially filled d orbitals. As we can see, scandium is not because it only forms scandium 3+, which doesn't have partially filled d orbitals. Titanium 2 does, so yes, titanium is. And so the answer here is gold and titanium, since scandium does not, and zinc has 3d10, which is fully filled. They are not partially filled, so zinc is also out. So the answer should be B. In question 7, what are the shapes of complexes? This one here and that. So this one here is tetrahedral. This is tetrachlorocuprate, as we can see, tetrahedral. And then this one here is square planar. So the answer should be C. In question 8, which is correct about standard electrode potentials? The first part says if Edexcel is proportional to natural log of K and natural log of ds total. This is wrong. It should be just ds total like we see here. So this is correct. E theta for the cell is proportional to natural log of K as well as ds total. B should be the answer. Natural log of cell is out, and here when you say proportional to ds surrounding, that is also wrong. In question 9, which reagents are mixed with hydrochloric acid to produce the benzene diazonium ion? They should be phenylamine and sodium nitrite, because these two react to give us nitrous acid, which is going to react with phenylamine to give us this product here. So the answer is A. And in part B, which reagents and conditions are used to prepare the yellow dye for phenyldiazenyl phenol from benzene diazonium ion? So this is the product they're talking about, and since it's being prepared from this, the other should be phenol. So I said phenol dissolved in an alkaline solution at 5 degrees. That is correct. In question 10, which sequence describes recrystallization? During recrystallization, we dissolve the crystals into a minimum amount of hard solvent so that all soluble impurities at high temperature dissolve while the insoluble impurities are filtered out. Then you cool down so that you can form the crystals, and after which the crystals are going to be filtered, and then you wash them with minimum amount of ice cold solvent. So based on those steps, C is the answer. Dissolve in the minimum volume of hard solvent, filter to remove the insoluble impurities, then cool and filter to remove soluble impurities. C should be the answer. In question 11, a synthesis of aspirin from phenol is shown. So we see this giving us that R is the intermediate part, and then finally we see a product. They've given us the corresponding relative molecular masses, and they ask what mass of aspirin is formed from 23.5 grams of phenol. So if this is the starting amount and they've given us 23.5 grams, I'm going to find the number of moles of this. So moles are the mass, which is 23.5, divided by 94, and I got 0.25 mole. So these are the moles present at the start of the reaction. Use the number of moles to get the theoretical moles of this. Since theoretical moles assumes 100% yield, they have the same number of moles since the ratio is 1:1. So the actual moles of the intermediate, I'm talking about the actual moles of these, not theoretical. Theoretical are exactly 0.25, but the actual are going to be due to 80% yield. So it's going to be yield equals to actual, which is unknown, divided by the theoretical times 100, and I got 0.2 mole. So the actual yield or the actual moles of these with 80% yield are going to be 0.2 mole. Now I'm going to use this actual to calculate the moles of the product. So when we get the theoretical moles of the final product, since the ratio is 1:1, the moles present are going to be exactly the moles of the theoretical product here, which is 0.2 mole. Then I will use 75% yield in order to find the actual moles at the end. So actual moles of the final product is using 75% yield. So 75 equals the actual divided by 0.2 times 100, giving us 0.15 mole. These are the moles of the actual final product. So I can multiply those with the molecular mass in order to find the actual mass, which is 27 grams. And so B is the answer. In question 12, an 8.4 gram sample of a hydrocarbon from 26.4 grams of carbon dioxide on complete combustion. What is the molecular formula of this compound? So they've told us the mass is 8.4 grams of the hydrocarbon, and then the CO2 formed is that. I can use this to find the mass of carbon. Since carbon dioxide has CO2, the composition from carbon is 12 over the 44 times the mass given here. So I got 7.2 grams, meaning the mass of hydrogen is going to be the original sample of the hydrocarbon, or the original mass of the hydrocarbon, minus the mass of carbon. So it's going to be 8.4 minus 7.2, giving us 1.2 grams. This is the mass of hydrogen, and that is the mass of carbon. So we're going to use these masses to find the number of moles and then the mole ratio. So for carbon, 7.2 divided by 12 gives us 0.6. For hydrogen, 1.2 divided by 1 gives us 1.2. So mole ratio is 1:2. So the empirical formula is carbon, hydrogen 2. And then we look here to find which is the molecular formula, since they said molecular formula. So this is empirical, as we've got here. The corresponding molecular should be carbon 6, hydrogen 12, because if you divide these, you get CH2, and D is the answer. In question 13, what are the volumes of oxygen required and carbon dioxide produced at room temperature and pressure on complete combustion of 5.8 grams of butane? When you use butane and burn it in excess oxygen, you get 4 carbon dioxide and 5 water. Of course, this is going to be 13/2 if you balance the equation. So I started off by calculating moles of butane, which are going to be 5.8, the mass given, divided by the MR, which was given here, giving us 0.1 mole. And the ratio of butane to oxygen, we can see it's 1 to 13/2. So meaning we can use the mole ratio to get the moles of this as 13/2 times 0.1, giving us that. So then the volume used, volume of this, since it's at room temperature and pressure, we know the molar gas volume is that. So volume should be the number of moles times molar gas volume, giving us 15.6 decimeters cubed. And finally, I can use a volume ratio. If this is 15.6, this is going to be 4 divided by 13/2 times 15.6. So that gives us 9.6 decimeters cubed, and so the answer is going to be A. In question 14, what is the repeat unit of the water-soluble polymer polyethanol? So polyethanol should be coming from ethanol, and this is the formula or structure of ethanol. So if I polymerize this, it becomes breaking the double bond and extending out, then putting the curly brackets on N. This is going to be what we have. So meaning the repeat unit is going to be B here. It's the only one that corresponds to what I've created here. In question 15, a repeat unit for a polyamide is shown, which is this one here. They say which pair of monomers makes this polymer. So the polymerization has taken place here as a condensation reaction took place between the NH2 here and the carboxylic acid. So if I hydrolyze this, I'm going to create this and that. And therefore the answer is going to be A, since we see these are 4 and these are 6. The others do not match what I've created here, so A should be the answer. In question 16, for compounds W, X, Y, and Z are shown. We see them there. They say which compound is an optically active amino acid. To be optically active, it means you have a chiral center, because this group and that group are the same. This carbon is now chiral. For compound X, that and that are the same, so this carbon is now chiral. And for Y, we can see this is chiral. For Z, this and that are the same, so this carbon is not chiral. Therefore, the answer is C, compound Y. And then they say which compound does not have the same number of peaks in the low resolution proton NMR spectrum and the carbon-13 NMR spectrum. So let's begin with the carbon-13. Here we have this carbon, one environment, the second environment, and then these carbons are identical. So here we have 3 carbon environments. If we compare the proton environments, we have 1. Then these protons and those are identical, and then 1. So we also have 3 proton environments. When we come to X, we have this carbon, the second carbon, and these 2 are identical. So 3 carbon environments. For hydrogens, we have 1. These 2 are identical, and the third. So again, 3 carbons, 3 hydrogen. For Y, we have 1 carbon, the second carbon, and the third carbon. So we have 3 carbon environments. For hydrogens, we have 1, 2, 3, and 4. So here we have 3 carbon and 4 hydrogen. Then we go to Z. This carbon and that carbon are identical, so 1. Then we go to 2 and 3. The protons, we have 1, which is identical to that. Then we have number 2 and number 3. So this is also not the answer. The only answer is going to be compound Y again. In question 17, asparagine is an amino acid, like we see here. They say what would be the structure of asparagine in an aqueous solution at pH 2? pH 2 is acidic, so the hydrogen from the dissociation of the acid is going to receive this lone pair on nitrogen, producing NH3. So the structure I got is this one here, structure D. Then in part B, they say in a high resolution proton NMR spectrum of asparagine, what would be the splitting pattern for the protons indicated by the arrow? When we look at these protons, this carbon has no hydrogen, but this carbon has 1 hydrogen. So the splitting pattern is going to be 1 plus 1, giving us a doublet. And so the answer is B. In question 18, the standard EMF ether cell of the cell shown was measured. So they've given us the corresponding electrode potentials and the equations. They say identify by name or formula the substance needed in the salt bridge, and the right-hand half cell include concentrations where appropriate. Although this concentration is not necessary, just say potassium nitrate. And then we go to electrode made of. So electrode B is going to be made of platinum. Because we have 2 ions from the same element but in different oxidation states, so if they are in solution, the electrode cannot be out of a metal with like for example ions, so it has to be something unreactive like platinum. And then solution containing the compounds. This is going to be, if we use iron 2, it's going to be 1 mole per decimeter cubed, and iron 3, for example iron 3 sulfate, is going to be 0.5 mole per decimeter cubed. So 1 mole of iron 3 sulfate produces 2 moles of iron, so in this case iron 3. So if we want 1 mole per decimeter cubed of iron 3, we'll use a half or 0.5 of this to produce double, which will be 1 mole per decimeter cubed. The next they say state why a salt bridge is used rather than a wire. A salt bridge is going to complete the circuit by allowing the ions to move into the corresponding half cell sides. So I said it completes the circuit by allowing ion flow, which maintains electrical neutrality. And in part B, write an equation for the reaction that would take place if current was allowed to flow through the circuit. State symbols are not required. Like I said already, this has more negative, so it's going to be to the left, and that is going to be to the right. So to balance this is going to go in that direction, receiving electrons, and this is going to be reversed. So zinc, which is a solid, is going to react with iron 3, and then we get iron 2 plus zinc ions as the product, Zinc is a solid. This is aqueous, aqueous, and then aqueous. So that is the final equation. Then in part C, they say under standard conditions, the E theta cell for this reaction is 1.53 volts. State what would happen to this value, if anything, when the zinc 2 plus solution in the half cell is diluted. Justify your answer. When we dilute, it means the concentration of zinc 2 plus is going to decrease, and this equilibrium is going to be driven further to this side, making this even more negative. And if this is more negative, it means when we calculate the E theta, this remains the same, but this is going to be a more negative value. So this minus a more negative value gives us a more positive E theta value for the cell. If you can see here, we usually say E theta for the cell equals the E right, which would be this one here, minus the E left. But since this is going to that side, the E left is even more negative. So if we subtract a more negative number, meaning the overall solution or the overall E theta for the cell is even going to be more positive. So I say diluting the zinc 2 plus decreases its concentration, shifting the equilibrium of that to the left, meaning more zinc 2 plus ions are going to be produced, and this half cell is more oxidizable. It has a more negative half cell value. As a result, the whole cell potential increases. You can see the explanation down here in more detail. Then in question 19, Grignard's reagents are used to increase the length of carbon chain in organic molecules. An outline synthesis of propanoic acid from ethanoic acid is shown. Propanoic acid has one extra carbon than ethanoic acid, and we see in the steps there is Grignard's reagent, so meaning there should be a halogen or alkane, more so in this step here. So usually we use bromoalkanes, so in this step we use 50% sulfuric acid plus potassium bromide to give us the hydrogen bromide, which is the reagent to convert this to that. And then in this step, to produce a Grignard's reagent, we're going to use magnesium in dry ether, giving us this. And then this is going to react with carbon dioxide. And then we hydrolyze in the presence of acid to give us the propanoic acid. So here they say step 1. They want us to complete the table. Step 1, reagents and conditions. In this step, we use a reducing agent, LiAlH4 in dry ether. Then step 2, the reagents are going to be 50% sulfuric acid and potassium bromide. And then name or formula of compound X. Compound X is CH3, CH2Br, like I've already explained. Then step 3, reagents and conditions, is going to be magnesium in dry ether. We are trying to make Grignard's reagent. And then formula of Grignard's reagent is that. And the final step, carbon dioxide followed by hydrolysis in acidic conditions. In question 20, this question is about some chromium compounds. Some reactions of chromium compounds are shown. So we see the layout. This is chromate 6, which is yellow, and then dichromate, which is orange. We can use acid and alkali to reverse in both directions, as you can see here. Then reaction 1, in this direction we are reducing. A suitable reducing agent, usually we can use zinc. And to oxidize, hydrogen peroxide is perfect. Chromium 3 is going to be, which is green, of course, will be obtained. And then in this case, chromium 3 becoming something purple, that is going to be in presence of excess ammonia. That is a ligand exchange reaction producing that product. So they say write the equation from reaction 1. Use the half equations from page 10 of your data booklet. State symbols are not required. So the half equations from the data booklet are this one here and that one there with their corresponding E theta values. Now, since here we have 6 electrons, we have to balance these to make them 6 as well. That's why I multiply this equation by 3 to generate this one. And then we can combine the two. To combine, we have 2 chromium 3 plus 3H2O. Now, since we have waters on both sides, here we have 6 and here we have 7, so we're going to remain with 1 water on the left side. And also we have hydrogens on the left here and hydrogens to the other side, so we will have 8 to the right side because they are more to the right than to the left. The electrons are going to cancel out, and then we'll produce all dichromate as well. So this is the final equation that is required. Then they say in reaction 2, dichromate reacts with a metal M in acidic conditions, forming chromium 3 and M2+. Identify a possible metal M, calculating E theta cell for this reaction with dichromate 6. Again, they want us to use the data booklet on page 10. So when I looked at page 10, possible metals, you could find magnesium, copper, because all these, they had more negative electrode potentials in comparison to that of chromium. So it means they will be oxidized as dichromate 6 is reduced to chromium 3. So using zinc, whose ether is 0.76 volts, and this is plus 1.33, we can see this is more negative, so this will be oxidized, meaning zinc becoming zinc 2 plus, and dichromate becoming chromium 3. So the ether value is going to be that minus that, giving us this. So zinc is a suitable metal. Because this ether is positive, that reaction will be feasible. Then they say give the formula of the species responsible for the purple color formed in reaction 3, naming the type of reaction that occurs. I've already written up there. This is the ligand substitution reaction or ligand exchange, and this is the product that is going to be formed. Then state whether or not the reaction in reaction 4 is a redox reaction and justify your answer. If we go back to reaction 4, this is not redox. This is +6 oxidation state, and that is +6, so not redox. There is no change in oxidation state. Chromium in chromate 6 and of course chromium in dichromate 6 are both +6 oxidation state. Then in part B, a double salt of chromium, which is that it has chromium 3, potassium, and sulfate ions. Deduce the simplest formula of this double salt. The easy way to decode this is, if it's chromium bonded to sulfate, it's going to be, this is chromium 3, so chromium 3 sulfate, and the other side we have potassium sulfate. To combine them together, we have 2 chromiums, and then we have 2 potassiums, but the sulfates are going to be 4 in total. Then get the smallest whole number ratio, divide by 2, we get K, divide by 2 Cr, divide by 2 sulfate 2. So this is going to be the final answer. And then they say the double salt also exists as hydrated crystals. When a sample of the hydrated double salt is heated until all the water of crystallization is removed, 56.74% of the original mass of solid remains. Calculate the number of moles of water of crystallization in 1 mole of the hydrated salt. Now, if 56.74 remains, it means whatever has gone away is going to be water. So the percentage composition of water in the original is going to be 100 minus that, as we can see here. So water removed is 100 minus that, giving us 43.26%. Now, if we are trying to get a ratio, we need the molar masses. So molar mass of the double salt, potassium, chromium, then twice the sulfate gives us that. And finally, we get the ratio of the anhydrous to the water, which should be 1 to X. This is percentage divided by MR, and this is the percentage divided by 18 for water. I got 0.2 to 2.403. Dividing through to get the smallest whole number ratio, I got 1 to 12. And so there are 12 waters of crystallization, or 12 moles of water crystallization. In part C, we require small amounts of chromium 3 in our diet as they are important in the breakdown of fats and many other body processes. However, too high a concentration of chromium 3 is toxic. Blood should not contain more than 4 parts per billion by mass of chromium 3. The concentration of chromium 3 in a blood sample is 1.345 times 10 power negative 7 mole per decimeter cube. Show by calculation that the chromium 3 level in the blood sample exceeds the safe limit. So we're going to look at that. They've given us 1 billion is 10 power 9. So I began by getting the mass concentration. Since we are given the molar concentration, I need to convert that to grams instead of moles. So mass concentration should be molar concentration times molar mass. So we know the molar concentration times for chromium is going to be 52. And then I got 6.994 times 10 power negative 6 gram per decimeter cubed. But 1 decimeter cubed is the same as 1,000 centimeters cubed. So I got this as my answer. If you divide through, then the concentration in parts per billion should be the mass in grams divided by the volume in centimeters cubed times 10 power 9. So this is mass divided by volume, which is that, then times 10 power 9, giving us 6.994 ppb as my answer. And since this is greater than the 4 ppb, this value is beyond the safe limit. Next, they say EDTA the ion has been considered as a potential treatment for chromium 3 poisoning. We see the structure of EDTA. This suggests how EDTA, of course the ion, would act to treat chromium 3 plus poisoning, giving a reason why EDTA would be preferred to other reagents such as 1,2-diaminoethane, which is that. This is a hexadetonate ligand. It forms dative covalent bonds around the central metal, allowing it to precipitate out of solution and we only need to use less concentration. So EDTA is a hexadentate ligand. It forms stable complexes with chromium-3, so it can effectively remove chromium-3 from the blood. It's preferred over bidentate ligands due to higher stability of the complex. It's more stable. In question 21, this question is about iron 2 sulfate. The electronic configuration for iron is shown, which is that. They say complete the electronic configuration for iron 2 ion in iron 2 sulfate. So if it's iron 2 plus, it has lost these 2 electrons, meaning the configuration remains only for the D, as those have gone away since they are the first to be lost. Then an aqueous solution of iron 2 sulfate is pale green in color. When left exposed to the air, the solution turns brown. This is due to oxidation by oxygen in the air, 2 turns to 3. Explain why this color change occurs. In your response, refer to your answer in A1. Our answer in A1 is about the electronic configuration. When we look here, we see iron 2 will have pairing, but iron 3, one of these electrons will be out. And this pairing or repulsion within the paired orbital is going to cause a difference in how electrons transition in iron 2 in comparison to iron 3. And so the light absorbed is going to be different between iron 2 and iron 3, and the light transmitted is going to be different, and the colors will be different. So I said on exposure to oxygen in the air, the pale green iron 2 is oxidized to yellow-brown iron 3, making the solution appear brown. From part A1, iron 3 is more stable than iron 2. Fe2 plus has 6 electrons in 3D, while F3 plus has 5 electrons. So here there is pairing and here there isn't. Presence of 2 electrons in the same orbital leads to repulsion affecting the D to D transitions. And like I said, so different amounts of light are going to be absorbed, or different wavelengths of light are going to be absorbed due to that gap between the lower D and the upper D. And then different wavelengths of light are going to be left behind. That's why we see different colors. In part B, they say many most killers contain iron 2 sulfate as the active compound. Potassium manganese 7 can be used to determine the amount of iron 2 sulfate present. In an experiment, 6.42 grams of most killer was transferred to a volumetric flask and made up to 250 centimeters cubed with distilled water. A 25 centimeters cubed portion of the solution was acidified and titrated with 0.00740 mole per decimeter cubed potassium manganese 7 solution. The equation for the titration is shown here. So I wrote some information from here below their corresponding particles. They say the mean titer was that, so we see volume and concentration for this and then volume for that. They say calculate the percentage by mass of iron 2 sulfate in the most killer. Give your answer to an appropriate number of significant figures. So I began by calculating the moles of potassium manganese 7 since we know the concentration and volume. So concentration times volume in decimeters cubed gave us that. When we look at the mole ratio, it's 1 to 5. So the moles of this in the 25 is going to be 5 times the moles of the manganate, giving us that. Then we go to the moles in 250. Moles of iron 2 in 250 should be these moles times 10, meaning moles in 25 times 10 gives us moles in 250. This is like scaling up. Then the mass of iron 2 sulfate in most killer should be the number of moles times the molar mass given here, 151.9, giving us this mass. So the percentage is going to be this mass divided by the original mass times 100, giving us about 15.5%. Next, they suggest why iron 2 sulfate is acidic when dissolved in water. When it dissolves in water, of course, there is going to be deprotonation, and that releases H plus ions. In question 22, compare and contrast the bromination of benzene and the bromination of phenol. Include equations in your answer. Detailed mechanisms are not required. Phenol is easily brominated in comparison to benzene because from phenol we have an OH group. This OH group is electron donating, and so it increases the electron density in here, making the ring more susceptible to electrophilic attacks. And when these reactions take place, we have position 2, position 4, and position 6, meaning 2,4,6 tribromophenol can be formed. In benzene, we need a halogen carrier. It could be aluminum bromide, iron 3 bromide, in order for this to take place, and it takes place under heated conditions. So I said both are electrophilic substitution reactions, but they differ in reactivity and required conditions due to the presence of the hydroxyl group in phenol. Benzene has a stable delocalized pi electron system, which makes it relatively unreactive towards electrophiles like bromine. To facilitate bromination, a halogen carrier such as anthrabromide is required to generate a stronger electrophile, which is Br+. The reaction is carried out under heated conditions. So we see bromine reacting with a halogen carrier, producing the electrophile, and then the other product, and this electrophile will attack the ring. So the reaction is the benzene with Br or in using the electrophile under heated conditions to give us that, and HBr. Then phenol, in contrast, has an OH group which donates a lone pair into the benzene ring, increasing the electron density at position 2, 4, and 6. This makes the ring most reactive and allows bromination to occur readily at room temperature without a catalyst. When phenol is treated with bromine water, it undergoes multiple substitution reactions to form 2,4,6-tribromophenol. It could be even just bromine. As we can see here, this bromination reaction with phenol is fast and decolorizes the orange bromine water, form a white precipitate. In contrast, benzene shows no visible change without a catalyst, and typically only one bromine is substituted under controlled conditions. In question 23, procaine is a local anesthetic that was commonly used until the end of the last century in dental procedures to numb the area around a tooth. So they said it is the molecular formula of procaine. I'm going to begin by removing everything I wrote. Now I've put everything back. We can see to count the number of carbons: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the hydrogens we have 1, 2, 3, 4. Here we have no hydrogens since the ring should be only connected to each carbon in the ring should only be connected to one thing. So since they already have things they're connected to, there is no hydrogen. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then 19, 20. Then nitrogens, we have that, and this one here, and oxygen is 1 and 2. So they should be what we have there. Then they say a possible reaction sequence to make procaine is shown. So we see this is forming methylbenzene, and of course it's going to be maybe we use a halogenoalkane and a halogen carrier. Then we go to nitration, concentrated nitric acid, concentrated sulfuric acid to this step. Then after we form a carboxylic acid on this group, then an acyl chloride. And then down here we see a reaction, we produce an ester bond, so there is going to be this acyl chloride and maybe OH, should be a reaction between an acyl chloride and an alcohol, so should be a hydrogen here. And finally we convert from here to here, meaning this is reduction using tin in concentrated HCl. So they say identify by name or formula the two reagents needed in step 1. Of course, I've already written them here, chloromethane and aluminium chloride. The next they say for step 2, draw the mechanism for this reaction, including the formation of a suitable electrophile and the regeneration of a catalyst, include Kali arrows. The reaction they're talking about in step 2 is this one here. I put it here so that we don't have to go back every time. So to generate the electrophile, nitric acid reacts with sulfuric acid. These two acids are concentrated to produce the electrophile and the other two products. And since the NO2 is positioned on carbon 4, the attack on the electrophile is going to be from down here. So electrons are donated to the electrophile, and then it binds, the hydrogen is exposed out, and the ring is broken. There is a positive sign inside. And then the next step, we see the hydrogen, the carbon-hydrogen bond breaking, returning the electrons into the ring. We form the final product plus the hydrogen that was lost. And then in the end, this hydrogen plus HSO4 minus to regenerate a catalyst. That is going to be our answer. Then next they say, for step 5, name the type of reaction taking place and draw the skeletal formula of the reagents needed to carry out this reaction. So this is the reaction they're talking about. Like I said already, this is an ester formed, so it should be OH. Just put a hydrogen here as we can see. So this reaction is esterification. Next they say identify by name or formula the reagents required in step 6. Step 6 was reduction. We need tin in concentrated HCl or tin and concentrated HCl. Then they say procaine contains 2 nitrogen atoms, one of which is a stronger base than the other. Yeah, we can see this and this. The lone pairs here are going to be incorporated in the ring, not so available to be donated, well, this is farther away from the ring, they are more available, so this is going to be the stronger one in comparison to that. This explains why the basicity of the nitrogen atom in procaine is different. Like I've said, the aliphatic amine, talking about this, is a stronger base because its lone pair is fully available for protonation. The aromatic amine, this one, on the benzene ring is weaker due to the delocalization of the lone pair into the ring, making it less available. Then they say procaine hydrochloride is made by reacting procaine with hydrogen chloride in a ratio of 1:1. Draw the structure of procaine hydrochloride, showing how the hydrogen ion attaches to the molecule. Now, if we go back here, we see this product here. If there is a hydrogen chloride, since there is a lone pair here to be donated, there is going to be a hydrogen binding there to form a nitrogen that is positively charged, and later the Cl- and the positively charged nitrogen are going to form an ionic bond. So the structure should be like that. This is positively charged after giving the lone pair to hydrogen, and then an ionic bond forms between the two. Explain why procaine hydrochloride is more soluble in aqueous solutions such as blood plasma than procaine. It has an ionic bond, so I said procaine hydrochloride is ionic. It contains a quaternary ammonium ion and chloride, which allow it to form an ion-dipole interaction or ion-dipole interactions with water, increasing solubility. As we saw, procaine is neutral, so less polar, and it's going to be less soluble in polar solvents like blood plasma. Then in part D, nowadays procaine has been replaced by lidocaine, a related compound as a local anesthetic in dentistry. Lidocaine is applied in 2.2 centimeters cubed cartridges that contain 44 milligrams of lidocaine. A typical adult dose is 1.5 centimeters cubed. Calculate the number of molecules of lidocaine present in a 1.5 centimeters cubed dose. They've given us the molar mass of lidocaine. 1.5 is going to contain 44 divided by that times 1.5, giving us 30 milligrams. So the moles of lidocaine in 30 milligrams are going to be mass divided by mR, which is going to be 30 times 10 power negative 3 to convert this to grams. So 30 times 10 power negative 3 grams divided by that. And I got 1.28205 times 10 power negative 4 mole. Then to find the number of molecules, it should be number of moles times Avogadro's constant, which is that times 6.02 times 10 power 23. And in the end, I got 7.72 times 10 power 19 molecules, rounded off to 3 significant figures. So this brings us to the end of question 23, as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.